The primary purpose of this video series is to explain how the learning progression method is implemented, with a special focus on the logistics of grading. I'm Elise Naramore, and this is part 2, in which I will explain what a practice is, how the practices are developed, and what they are used for. Practices describe behaviors shown by students as they engage with the skills and knowledge specific to your discipline. This is distinct from units, topics, and content. Content is the vehicle, while the practice is the roadway, with mastery at some defined level being the destination. I am a science teacher, specifically a physics teacher, so I will describe my practices. Each teacher has an umbrella under which they choose their content. This may be a district curriculum, a state curriculum, and/or a national guideline. It can also be influenced by state or commercial exams. In our case, the Next Generation Science Standards publish disciplinary core ideas, science and engineering practices, and cross-cutting concepts, all meant to help science teachers guide students towards building a cohesive understanding of science over their K through 12 years. I can go onto their website to identify what my high school physics classes are expected to have mastered by the time they have exited my class. The 8 practices we are supposed to use, as mandated by the NGSS, are listed in the right column. The problem is that they are written for teachers and are difficult to use for assessment as written. So we have used them as a guideline, but breaking them into more manageable chunks that are easier to understand and use in our classroom. I want to show you how our 10 practices listed in that left column incorporate those that are mandated. NGSS has asking questions and defining problems, which we use in 2 practices, experimental design and the engineering design process. NGSS has developing and using models, which we evaluate in 2 practices, problem solving and the engineering design process. NGSS uses planning and carrying out investigations, which we evaluate in experimental design and the engineering design process. NGSS uses analyzing and interpreting data, which we actually do in 4 different practices: data analysis, interpreting graphs, creating graphs, and the engineering design process. NGSS has using mathematics and computational thinking, which we evaluate in just 1 practice, problem solving. They use constructing explanations and designing solutions, which we break down into 2 practices, creating explanations and making predictions, and the engineering design process. In engaging in argument from evidence, we broke that into 2 practices, creating explanations and making predictions, and arguing a scientific claim. Lastly, we've got creating, evaluating, and communicating information, which we evaluate in 3 practices: using feedback, creating explanations, and making predictions, and graph interpretation. As you can see, I evaluate all of the Next Generation Science Standards, just rearranged under different titles. Again, why did I do that? In brief, NGSS is worded for educators, not for students. My practices are for students. They have to understand the languages we are using so that we can communicate fully. So let's examine just 1 in some more detail: designing and carrying out investigations. So you can see how we developed our language. The NGSS has terrific criteria that I almost uniformly appreciate and agree with. However, their language is often impossible for students and parents to comprehend. I wanted to pull out the essence of their criteria without getting too caught up in the formal educational talk, which can be opaque and too dense. Therefore, out of their 3 bullet points, I created my own much simplified criteria. For example, you ready? Instead of formulate a question that can be investigated within the scope of the classroom, school laboratory, or field with available resources, and when appropriate, frame a hypothesis, that is, a possible explanation that predicts a particular and stable outcome based on a model or theory. I wrote, ask a testable question. Instead of decide what data are to be gathered, what tools are needed to do the gathering, and how measurements will be recorded, I wrote, collect accurate data using appropriate tools, and so on. So here's a description of each of our 10 practices. I want to just read them through so you can take some time to understand the purpose of each one. When you hand in a lab report, you will get a score on each of the following 4 practices. Experimental design has the lab question, the methods and materials, the data and observations. The goal is to communicate what and how you did the data collection with enough detail so that someone else can follow your work easily. Data analysis in a lab context has a goal of communicating what and how you did the data analysis with enough detail so that someone else can follow your work easily. A discussion about sources of experimental error is essential. The other parts of the analysis section may include any or all of the following: graphing, problem solving, sample calculations, and/or quantitative error analysis, all of which I will teach you how to do. Arguing a scientific claim includes the claim, the evidence, and the reasoning. The goal is to communicate the answer to the lab question, the best evidence you have for that answer, and how those results relate to the known physics theory. Using feedback is where you annotate your lab, highlighting the changes you made from the previous lab. The goal is to communicate what changes you made, why you made them, and how you have improved over time. So when you hand in a quiz or a test, which I call checkpoints, you will get a score on each of the following 4 practices. First, creating explanations and making predictions. The goal is to show what physics you know and can apply from the current unit of study. The physics can take the form of overtly stated definitions, laws, mathematical models, equations, or relationships. For the next one, problem solving, the goal is that when you solve a scientific problem, you should show the process you used. This problem solving process includes givens and variables on a labeled sketch or illustration, relevant diagrams, the equations used, numbers plugged in, and an answer to the question asked with units on all values. Graph interpretation has a goal of overtly using features of the graph accompanied by an explanation to demonstrate your understanding of the physics. Features might include coordinate pairs, slope, graph shape, area, and/or y-intercept. When appropriate, a mathematical model is developed or interpreted. Some of these are more sophisticated than others, depending on the question. Graph creation, the goal is to overtly create a graph including all relevant features. This includes axes labeled with variables and units, a trend line, a descriptive title, plotted points, and any given or reference values on the axes to scale when appropriate. An overtly stated physics relationship is presented in the form of theory and/or mathematical model. So that's what you need for a test. When you hand in a project, you will get a score on each of the following 2 practices. First is engaging with content. The goal is to overtly encourage and develop creativity. Creativity requires flexible thinking, originality, fluency with concepts, and elaboration. The engineering design cycle's goal is to solve a real-world problem, generally by building something. The steps of the engineering design process include asking questions, brainstorming ideas, planning solutions, creating a design, testing and evaluating, then repeating this process through as many iterations as possible in the time provided to improve the product. You document all of your progress and thinking in a journal. To close, one of the most important features of the learning progression method is what I can glean from student results. As I use the learning progressions, I can see what's missing or not working or where the students are struggling. I can then address those issues by making adjustments to unit targets, the language, the order, or the expectations, so our practices have evolved as needs become apparent. Students aren't expected to get the practice all in one go. We set benchmarks or target levels for each unit, which are discussed much more in Module 8. The details of each practice are spelled out in the learning progressions, which is the focus of the next video.